We're going to be looking at question 19, June 23 paper. Before we do this, we're just going to clarify something from the last video on question 18. And I got a little bit stuck on the gradient. I was trying to link the graph with the expression, which was the wrong thing to do. In GCSE, we've learnt the expression y equals mx plus c. And in here, what we've got here, our y is our delta g, our mx, m is the gradient, and x, in this case, is the temperature. The gradient is actually entropy, and there's a minus if we rearrange the equation, and the y-intercept is our delta H value. So we just rearrange them. So actually the gradient is delta S, but there's a minus delta S. To get delta S on its own, we need to multiply it by -1 to get rid of that minus sign. And we also multiply it by 1,000 to convert kilojoules into joules to get our entropy change value. I hope that makes sense. So we're using the y equals mx plus c to determine the entropy change of a delta G free energy versus temperature graph. Looking at question 19, this question is to do with equilibrium constant and to do with partial pressures. So we've got our equation here. A sealed flask containing this much initial moles of NO2 is heated to a constant temperature and allowed to reach equilibrium. At equilibrium, 5.4 moles of NO2 remain, and the total pressure is 5 atmospheric pressure. Determine the value of Kp, give your answer to 3 sig figs, include the expression for Kp and the units for Kp. In this question, if we just 2NO2, N2O4, you see if we use the ice table, initially we've got 6 moles of this, of NO2, 6 moles. At equilibrium, it tells us that there's 5.40 moles remaining. That means there's a change of 0.60. The ratio is a 2 to 1 ratio. That means if 0.60 moles is being used up, half of that is going to form 0.30. So we divide that by 2. Initially, we had 0 moles, and at equilibrium, it means we will have 0.30 moles. Now, we need to work out the mole fraction because we're dealing with partial pressures. The mole fraction will be the mole of the substance at equilibrium divided by the total number of moles, which is 5.70. This will be 0.30 divided by 5.70. And if we multiply the total pressure, which is 5.00 atm, that gives us our partial pressures. We can give answer to 3 sig figs, 4.74, and the other one will be 0.3 divided by 0.26. Something to bear in mind that if you add these up, it will give you the total pressure of the system is supposed to add up to 5 atm, which it does. So we've got our partial pressures. We need to write down the expression for Kp. It's always products over reactants. We use P and we use curved brackets. So products is N2O4, products over reactants. Our reactant is NO2, but because there's a big 2, we raise that to the power. And so use plugging in the values, this is going to be Kp will equal 0.26 divided by, actually, just to be a bit more accurate, 263. 3 sig figs is a good accuracy to work towards. 4.74 squared. The answer is 0.0117. And the units, you see the units is an ATM. So what we've got here, we've got ATM over ATM squared. So the units will be ATM. The units will be ATM to the -1. Yep, ATM to the -1. And if you're a bit unsure about that, you see that cancels out with that, and you're dividing by ATM, atmospheric pressure. That's why it's to the -1. Moving on. This is interesting. You say the sealed flask, and if it helps, I'm going to just rewrite the equation. N2, NO2, two of those, N2O4. The Ford reaction is exothermic, so we'll come back to that. Ford reaction is exothermic, making the reverse reaction endothermic, and they are both gases. If we look here, it says the sealed flask is then heated to a higher temperature at an increased pressure. So we're doing two things. Explain why it is difficult to predict how these changes in reaction conditions affect the amount of N2O4 formed at equilibrium. You see, if we were to, by raising the temperature, raising the temperature, the equilibrium will shift. Equilibrium will shift to the left-hand side. And why is that? As the reverse reaction is endothermic. Endothermic, by raising the temperature. This is going to shift to the left. Now, if we were to, by increasing, sorry, this was increasing temperature. By increasing pressure, the equilibrium, you've increased the pressure, it's going to try to reduce the pressure, counteract the pressure. The equilibrium will shift to the right-hand side. Why? As there are fewer number of moles of gas. Pressure doesn't affect liquid or solids, it's the gas, few moles of gas. Now you see, you get 2 marks for those statements, but why is it difficult to predict? Because we don't know, you've got 2 opposing effects, and you don't know which effect is contributes more or less. They could cancel out. They oppose one another. They may not be the same size. There's a variation on possible answers that you can give. The last part of this question is a lovely PV equals nRT question. In this question, it says N2O4 reacts fully with oxygen to form a different oxide. Different oxide of nitrogen as the only product. Okay, so only one thing is forming. Oxide A. Oxide A is collected and cooled at this temperature, at this pressure. It occupies this much volume, and this is the mass of it. Calculate the molar mass. So here, we're going to use the expression PV equals nRT. The pressure is 101 kilopascals, so we convert that to pascals. Volume is 74, and to convert that to meters cubed, we divide it by 1,000,000. N is going to be mass of the gas given in the question over the mR, which we're trying to work out. R is 8.314. It's given to you in the data sheet, but it's worth remembering. And the temperature is 75 degrees Celsius, but we need to convert that to Kelvin. And so by rearranging, N is equal to PV over RT. Let's work this out. N is equal to 2.583 times 10 to the minus 3. And you see, we know that mass divided by the number of moles gives you the mR. So 0.280 divided by what we just worked out. And the answer is 108.4. 108.4. And the molecular formula. So really, we want to see what's the closest nitrogen oxide that gives you the formula of 108. Nitrogen is 14, so 14x plus 16y. And it's really a game of trial and error. So we could try what's the easiest? How can you determine what the formula would be? So NO is 30. We could so how many how would you how well the mark scheme says N205 is the nearest, has an MR of 108. Is there an easier way to do this? 108. I think it's a game of trying to play trial and error and see which one matches. Try with one nitrogen and all oxygen. Not entirely sure on that one, ladies and gentlemen. But this is the answer, main answer. They do allow ECFs, error carried forward. They'll probably allow other combinations of nitrogen and oxygen, but I just can't think of an easier way to help you determine that molecular formula without trial and error. With that, I'll see you next time. Thank you very much.